Hello students, today's class we are going to see about the transmission line theory. So first we are going to see what are the transmission line parameters in transmission line equation. So generally transmission lines are used at a low frequency as well as the high frequency. So for power distributions, you use the low frequencies, and for communication purpose, we use the high frequencies. So transmission lines can be commonly used in both the low frequencies as well as the high frequencies. So there are many types of transmission lines. So some of the types of transmission lines are twisted pair cables and coaxial cables. So usually coaxial cables are used for computer networks. Nowadays, we are moving towards the fiber optic cables. So in a transmission line, basically we have 2 or 4 parallel conductors which are used to connect the source to the load. So the examples of source are hydroelectric generators, a transmitter, and if you say about the load, a factory or an antenna. And if it is a typical transmission lines, which includes the coaxial cables, the two-wire transmission line, the parallel plate or the planar line, or a wire above the conducting medium, and a microstrip line. So these are some of the types of transmission lines. This is how the coaxial line looks like. So you will have an outer shielding. Inside you will have the golden strips of leads. So usually whenever there is a power cut in our home, we used to check the fuse. So in the fuse, we use for replacing the fuse wire, we generally go for the coaxial cable. We remove the outer shield and only the strips alone we will take it. Around 5 to 6 strips lines will be there, and those strips will be taken and we will be using for the fuse. And this is called as the two-wire line. And we know the twisted pair cables. So we are aware of the twisted pair cables. So in all the houses we use the twisted pair cables, and we have the planar line. This is how the planar line looks. And then we have the wire above conducting plane and the microstrip line. So now we're going to see about the transmission line parameters. So a transmission line is described in terms of its line parameters. So the parameters are R, L, G, and C. So R is nothing but the resistance per unit length. L is nothing but the inductance per unit length. G is the conductance per unit length, and C is the capacitance per unit length. So all these parameters R, L, G, and C are uniformly distributed along the length of the wire. And this R, L, G, and C are called as the primary constants because they are assumed to be independent of frequencies. So we have also the secondary constants. The secondary constants of the characteristic impedance is Z0, the propagation constant gamma, the attenuation constant alpha, and the phase constant beta. So all these constants are somehow fixed at one particular frequencies, but these values can be changed as the frequency changes. So we know the general formula of velocity. Velocity is nothing but the distance traveled by time taken. So what is the distance traveled? I have related the distance traveled with that of the wavelength, and the time taken I have written t is equal to 1 by f. So I have written the time taken in terms of the frequency. So how do I write the distance traveled in terms of lambda? Because we know lambda is the wavelength. How the wavelength and the distance traveled is related means, so wavelength is nothing but the distance between the 2 points along the line at which the current or voltages differ in phase by 2 pi radians is called the wavelength. So we have here velocity is equal to lambda by 1 by f. So I can write it as v is equal to lambda into f. So this lambda can be written as 2 pi by beta. So how this 2 pi comes? Because the definition of wavelength is the distance between the 2 points along the line at which the current or voltages differ in phase by 2 pi radians. That's why you have this 2 pi over here. So therefore, we can write 2 pi f as omega, nothing but the angular frequency. And therefore, the velocity can be written as omega by beta, where beta is called as the phase constant, and it is nothing but the radians per unit length of the line. Now comes the propagation constant. We know the general notation of propagation constant. It is gamma. So gamma can be written as alpha plus j beta, where alpha is the attenuation constant and j beta is the phase constant. Gamma can also be written in terms of impedance and admittance. That is square root of Z into Y, where Z is called as the impedance and Y is called as the admittance. Now we'll see what do you mean by the characteristic impedance. So characteristic impedance is represented by the notation Z0. So characteristic impedance is nothing but the ratio of the positively traveling voltage wave to the current wave at any point on the line. So Z0 is nothing but the characteristic impedance, which is given by square root of Z by Y, where Z is called as the series impedance and Y is called as the shunt admittance. So Z can be expressed as R plus J omega L. How do you write it as R plus J omega L? So here this R and L are in series and C and the capacitor and the conductance are in the parallel. So the impedance can be written as, can be said as the series impedance. So it is R plus J omega L. Similarly, the Y is called as the shunt admittance. It is nothing but the G plus J omega C. So we know that Z0, the characteristic impedance is equal to square root of Z by Y. So in the place of Z, I have replaced with R plus J omega L. And in the place of Y, I have replaced with G plus J omega C. So I can write the characteristic impedance as a real part and the imaginary part. So that is R0 plus JX0. So reciprocal of the impedance, we know that is called as the admittance. Therefore, Y is equal to 1 by Z. That is Y0 is equal to 1 by Z0. So we have two cases over here. One is a lossless line. The other one is the distortionless line. So the condition to be a lossless line is your resistance is equal to conductance is equal to 0. This is the condition to be a lossless line. So we know that the impedance Z is equal to R plus J omega L. So when you substitute the value of R is equal to 0, therefore you get Z is equal to J omega L. Similarly, in the shunt admittance, Y is equal to G plus J omega C. The condition for to be a lossless line is G is equal to 0. And therefore, we can write Y is equal to, making G is equal to 0, Y is equal to J omega C. Now your Z0, that is the characteristic impedance is nothing but square root of Z by Y. So your Z is J omega L and your Y is J omega C. So the common terms J omega will get cancelled and therefore you'll get square root of L by C, which is nothing but your R0. So the impedance, you can also write it as the characteristic resistance. So your characteristic impedance is purely resistive in nature. We have also another formula called propagation constant gamma. So gamma is equal to alpha plus J beta. So where alpha is the phase constant and beta, alpha is the attenuation constant and beta is the phase constant. We can also write the propagation constant in terms of square root of Z into Y. So when you substitute the values of Z and Y, that is replacing the Z by R plus J omega L and replacing the shunt admittance by G plus J omega C. So you will get, we know the condition for the lossless line is R is equal to G is equal to 0. So this R part and G part will get cancelled and therefore you'll be getting J omega L into J omega C. Therefore, it becomes square root of J square omega square LC. So here the square root is there and here the square is there. So it gets cancelled and therefore the common terms, if you take it outside, it becomes J omega square root of LC. So this is an imaginary part because it is associated with the J term. So therefore, we can wind up alpha is equal, gamma is equal to alpha plus J beta. So that gamma result you got in terms of a complex quantity. So that means the imaginary part alone, you got it. Therefore, we can wind up your attenuation constant is equal to 0 and your phase constant beta is equal to omega root LC. Now comes the velocity formula. We know velocity can be written in notation either small v or small v. So velocity is nothing but the angular frequency divided by the phase constant, that is omega divided by beta. So I'll substitute the value of beta over here. Beta, we got it as omega square root of LC. I'll substitute over here. And therefore, this omega and omega will get cancelled. And therefore, you'll be getting 1 by square root of LC. So it is nothing but the, already we saw the velocity formula, the other one velocity formula with respect to the wavelength. So it is nothing but lambda into f. So the second special case is the distortion line. So the condition for the distortion line is R by L is equal to G by C. So this is the condition to be a distortionless line, not distortion line, distortionless line. So now we'll see the characteristic impedance. So the characteristic impedance, the basic formula is Z0 is equal to square root of Z by Y. We know Z is equal to R plus J omega L and Y is equal to G plus J omega C. So for my convenience, I just take the R outside and G outside in the denominator so that it becomes R upon 1 plus J omega L divided by R. Again, if you solve this, again this equation comes. Similarly, the denominator G taking as outside. So I'll get G upon 1 plus J omega C divided by G. So since we know R by L is equal to G by C, so we'll write, if you solve this equation, we'll get square root of R by G, or else we can write square root of L by C. Because we can replace R by L as G by C, or else G by C as R by L. In such a way, either your equation becomes either in terms of R by G or in terms of square root of L by C. So we know that the characteristic impedance is nothing but the real part and the imaginary part. And therefore, the solution, what we got for the characteristic impedance is a real part. We don't have any imaginary part over here. And therefore, your R naught will be square root of R by G, or else you can write in terms of L by C, square root of L by C, and your imaginary part will be equal to C. Now we'll see the propagation constant. So propagation constant is denoted by the symbol gamma. We know the formula gamma is equal to square root of Z into Y. So just substituting the series impedance R plus J omega L and substituting the shunt admittance G plus J omega C. And therefore, just for convenience, we take R outside and here G outside. So it will become like this. And therefore, taking the common notations over here, RG outside I have taken, and therefore it is 1 plus J omega L divided by R and 1 plus J omega C divided by R. So here already a square root is there. So taking this RG outside and therefore solving these equations, you'll get square root of 1 plus J omega C by G the whole square. That is substituting this L by R in terms of C by G, and therefore you'll get the square term over here. Therefore, square root of RG upon 1 plus J omega C by G, because this square root and this square will get cancelled. So this is nothing but the propagation constant. Propagation constant can also be written in terms of alpha plus J beta. So here the real part will be square root of RG and the imaginary part will be square root of RG upon omega C by G. So cancelling out the possible terms, we get alpha is equal to square root of RG and beta is equal to omega into square root of NC. Now we'll see the velocity for the distortionless line. So the basic formula for velocity is U, or a small v we can use for velocity. So which is equal to omega by beta. So we know the beta value. So substituting in this beta, this omega is square root of LC. So the possible terms to be cancelled out is omega, and therefore the velocity will be equal to square root 1 by square root of LC. And velocity can also be expressed in terms of wavelength. It's nothing but the lambda into L. So we have seen two special cases. One is the lossless line and the other one is the distortionless line. So what are the properties of both these things we'll see. So the phase velocity, what you got, the phase velocity is the V. Okay, is independent of frequency because the phase constant beta is linearly dependent on the frequencies. And when you see both the velocity and the characteristic impedance of lossless line and the distortionless line, both the equations will be same. That is one of the property. And a lossless line is also a distortion line, distortionless line, but a distortionless line is not necessarily to be lossless. And we had a summary over here for the transmission line characteristics. So for the general case, your gamma is nothing but alpha plus J beta, where alpha is the attenuation constant and beta is the phase constant. It can also be written, the gamma in general case can also be written as square root of Z into Y. So in the place of Z, I have replaced with the series impedance. In the place of Y, I have replaced with the shunt admittance. Similarly, the characteristic impedance in general way of writing this is Z naught is equal to R naught plus JX naught. Or else we can also have another formula, Z naught is equal to square root of Z by Y. So replacing in the place of Z R plus J omega L and the shunt admittance G plus J omega C, we get the characteristic impedance. This is how the general case you will write the propagation constant and characteristic impedance. And we have seen the two special cases. One is for lossless, the other one is for distortionless line. So for lossless, the propagation constant gamma is equal to 0 plus J omega square root of LC. So the meaning is your attenuation constant will be equal to 0 and the phase constant will be omega square root of LC. Similarly, the characteristic impedance for the lossless line is square root of L by C. And the other special case is the distortionless line, in which the propagation constant is nothing but gamma is nothing but square root of Rg plus j omega square root of Lc, and where the attenuation constant alpha is square root of Rg, and the phase constant beta is nothing but square root of Rg into omega into Lc. And the characteristic impedance for the distortionless line is the square root of L by C. So the two common parameters for both the cases, lossless and distortion line, is the characteristic impedance and velocity equation remains the same for both the special cases. Thank you.